let's give you a quick review for previous class. In previous class, actually, we introduced three different types of diffusivity based on different mature systems and also different observation coordinate. And actually, in most of case, when you have a diffusion couple, the diffusivity which we can measure is we call the interdiffusivity. And actually, this diffusivity, based on this equation, actually interdiffusivity is concentration dependent diffusivity. It will change with the composition of the component. And next, we are going to introduce you what's the Kirkendall effect. What's the Kirkendall effect? Actually, when the Kirkendall effect happens, the mass transport of two components with dissimilar diffusion rates in the alloy or reaction systems, in these kind of conditions, you can observe the Kirkendall effect. So let's take an example here. If we have a AB diffusion couple, and as you know, because we have AB diffusion couple, right? In this case, when the JA is larger than JB, then you will get the vacancy flux toward to left-handed side to reach or to allow the net flux. The total net flux equals to 0, right? So we get the JB plus JV equals to JA. So actually, under these conditions, we do have two different dissimilar diffusion rate in our system. So as you take this diffusion couple and heat up to a high temperature to allow the diffusion happens. So we believe you are going to observe the Kirkendall effect. So what are the Kirkendall effects? There are two characteristics to confirm the Kirkendall effect that happen on your system. The first one we call the Kirkendall void formation, which means that you are going to observe some voids form in this case would be you can observe some void form in A materials due to you can observe the vacancy flux toward to left-handed side. So you are going these vacancies, as long as this vacancy accumulate together will growth to form the void, and the void will be present inside material A. And the other characteristic will be we call the plane shift or Kirkendall shift, which means the interface due to the JA larger than JB. So that means the more A move to the right-handed side, this will push this interface toward to left-handed side. So the interface is going to shift toward. It's going to shift under these conditions. We call this is a Kirkendall shift. So let's take the zinc and copper, this diffusion couple as an example. When we heat up the zinc-copper diffusion couple, then when we heat up to a high temperature and when the diffusion happens, then you can observe what and here we confirm that the flux of zinc is larger than the flux of copper. So under this case, you can observe the void form in zinc, and also there's interdiffusion in between, right? So you can observe the zinc copper alloy, and in this case, some people call it as a brass. And we also can observe the interface shift to the left-handed side to here. So this is we call the Kirkendall effect. So this is a schematic, right? So I'm going to show you some real experimental results. So the same idea, we have the zinc-copper diffusion couple, but we put the marker in between zinc and copper. So we put a marker in between at the interface. And when we annealing this diffusion couple at high temperature for several hours, then allow the diffusion happens. So as a function of time period, you can observe the marker disappear because markers move downward. So you cannot see the marker anymore. And the second thing is you can observe the thickness of the brass get thicker and thicker as a function of time. Okay, so this is the real data. So if you check the schematic here, the same idea, because there's a vacancy flux to downward, so you can observe some void form in the zinc material, in the zinc side, so we can observe the void formation. And the interface actually is moved to downward. Okay, and in the meantime, we can observe the brass get thicker and thicker, and this result also confirm what we predict in previous line. So, additionally, if we have a copper and tin, we have a copper and tin into a diffusion couple, or some people call it a tin and silver solder on the top of copper. Then, due to also the flux of copper is larger than flux of tin, so let's merge the vacancy flux downward, right? So here we observe some void form at the copper side, and also we can observe there's a alloy, the copper and tin alloy form in between these two materials, right? So this is another examples here. So some people probably, so I'm going to introduce you. Yes, you observe the Kirkendall effect in diffusion couple. Are there any other material systems you also can observe the Kirkendall effect? So next, I'm going to show you the other examples is related to the metal oxidation. So what we have is we have the copper substrate in the beginning, and we try to flow the oxygen gas to oxidize this copper substrate. So in order to get the thick oxide layer, so we need to evaluate what's the mechanism behind here to have a thick oxide layer. So the orange atom means the copper, right? And how to get the oxide layer on the top of the copper substrate. So probably some people will mention that either the one possible mechanism is the metal ion is going to move upward, move to the surface to react with the oxygen molecule. This is one possible mechanism, right? And the second possible mechanism would be the oxygen molecule is going to diffuse through the oxide layer until it reaches the surface, until it reaches the react with the copper atoms. So either metals diffuse out or the oxygen diffuse in through the oxide layer, right? So in order to determine which mechanism really happens in this case, the first thing you need to consider would be which flux is faster. So after serious investigations, no matter if you can check the literature or something, the flux of this copper is larger than the flux of oxygen molecular inside this oxide layer. So based on this, we also have the dissimilar flux, right? So in this case, in order to reach the total net flux equals to 0, so we definitely have a vacancy flux downward. And so in this case, you can expect it you can confirm that this is a Kirkendall effect happen in the process of metal oxidation. And if we want to investigate this phenomena in micro scale, let's take a look at what happened inside these materials. First of all, you already confirmed that this is Kirkendall effect. So in this oxidation process, definitely you can observe the void formation, right? So why you can observe the Kirkendall void and void formation? The reason here is the metal moves to the surface of this substrate, so that it will left a vacancy here. So as the vacancy, there are a lot of vacancy presented, then they probably will accumulate growth to form the void. So this is the mechanism how the void form in the copper side. And the other characteristic for Kirkendall effect, we will say will be the plane shift or Kirkendall shift. Means this interface will shift downward, right? So why this plane is going to shift to downward? The reason here will be what? Yes, we have a vacancy here, right? But vacancy, instead of accumulate to form the void, probably this vacancy also can diffuse through these materials and to replace the atoms on the edge dislocation. So what's the edge dislocation? As you know, there's extra atoms presented inside these materials. So we assume here it was edge dislocation here. So the vacancy probably will be diffused to replace the atoms locate at the edge dislocation. So we become here, right? As long as we have enough vacancy, all the vacancy, and this vacancy replace all this whole edge dislocations. So this edge dislocation is going to disappear, right? So this will drive the plane shift downward. So in this case, you know how the void formation, how you can observe the plane shift. But next question I'm going to ask you is, in what kind of condition you have chance to observe more void instead of plane shift? So I will say more void, that means the vacancy flux. The vacancy flux must much larger than dislocation site. That means the JV is quite large. And why it must much larger than dislocation? That means because we have too many vacancies. Then this vacancy too many, so probably part of them will replace the atoms on the edge on the dislocation site, but we still have more vacancy, right? Under this case, then if the void formation energy is low, so that means the vacancy is easy to accumulate and form the void, and the other is the growth rate of void is much faster than the diffusion rate of vacancy through the copper materials. So under these situations, then you can observe more voids than the instead of a plane shift. But on the other hand, in what kind of conditions you have chance to observe more plane shift instead of more void form at the copper side? Probably that means if you don't observe the void, that means that implies that the vacancy flux is small, and most of vacancy diffuse through material to replace the atoms on the dislocation side. So that means we did have enough dislocation site. And the void formation energy is high, so that means vacancy is not easy to form the void. And the diffusion rate of the vacancy is much faster than growth rate of void. So under these situations, then you can observe more void or more plane shift instead of more void form as inside your materials. Okay, so now you have some concept about, what's the Kirkendall effect and what are the characteristics of the Kirkendall effect, right? And also know how the mechanism for the void formation and also the plane shift. So next, we are going to spend like several slides to introduce the applications of Kirkendall effect. That means how can we the possible potential applications of Kirkendall effect. So first applications for Kirkendall effect would be you have chance to know the diffusivity, which diffusivity is larger by using the Kirkendall effect. So now you have a diffusion couple, which is the copper zinc alloy bonded with copper. And also we put the markers in between these two metals. When we heat these materials up and allow the interdiffusion happens, then we observe the markers shift toward to left-handed side. So we can understand what the diffusivity of zinc and the copper, which one is faster, right? Because the marker shift to left-handed side, which means the J zinc is larger than J copper. So by using this idea or this Kirkendall effect, you can know the difference of the diffusivity for your interesting components. Okay, so next I'm going to introduce you the how we use the Kirkendall effect in material synthesis, especially synthesis some hollow nanoparticles and some hollow nanowire. So we are going to introduce you how to form the hollow nanoparticle and nanowire through the narrow-scale Kirkendall effect. So first of all, we are going to talk about the hollow nanoparticle. So in the beginning, actually, we are going to have this kind of core structure. The core actually is the material A, and the shell actually is AP alloy. Sorry, it's AP alloy. Okay, and as we know, the JA is larger. So JA is larger, so you are going to have a vacancy flux toward inside, to the inside of this nanoparticle. So when you heat this kosher structure up, then a lot of diffusion happens. JA is larger, so you can get the vacancy toward to inside to these nanoparticles. So you will get some void form in material A like this. And next, if you try to heat this material up, that means the diffusion still happens. Then this small void will accumulate to get the larger void. So you have chance to either form this kind of structures. So the difference between this one and this one would be what's the difference to allow you to have these different structures of hollow nanoparticle will be depending on the diffusivity of material A and also the surface diffusivity of material A and also the diameter of this nanoparticle we talk about. So you have chance to get these two different structure of nanoparticles. And if you want to, some people also play with these structures. For example, like some people use this structure and you ended some chemical reactions to etch the surface of this AB alloy to make this gap. So now you got these structures of these narrow Haro particles. Then some people also added the third materials inside to form the composite of nanoparticle. This is what you can do. Oh, some people also try to use some chemical to etch all these A materials out. So you can get this kind of nano structure, Haro structure of nanoparticles. So by using the Kirkendall effect, nanoscale Kirkendall effect, you can have different structures of Haro nanoparticles. Okay? And you can play with that. No matter, you can use this for drug delivering or for catalyst studies. Okay, so next I'm going to show you the formation of nanowire through the Kirkendall effect. So in the beginning, we pre-synthesis the zinc oxide wire, and the size here is around 10 to 30 nanometer. The diameter and the length actually is 2 centimeter long. And we try to use the ALD to deposit a conformal layer of alumina to cover zinc oxide nanowire. Then we are going to put this material into the oven to heat them up to 700 degrees C for 3 hours. Due to the flux of zinc oxide, the direction will be upward. So you will get the flux of vacancy, the direction of flux of vacancy downward, right? So that's why they can successfully to synthesize the zinc alumina nanotube by using this nanoscale Kirkendall effect. So I'm going to give you a quick summary of the diffusion and Kirkendall effect. Diffusivity is defined by Fick's law, and you also can say what's the diffusivity? It's the flux per unit concentration gradient. Just simply move this to the left-hand side. So it means the flux per unit concentration gradient. And you can simply divide the diffusivity into self-diffusivity, intrinsic diffusivity, and interdiffusivity according to the material system and also the observation coordinate of your materials. And that's a very important principle. Actually, is the total net flux should be equals to 0 in the crystal frame, and that will maintain the volume fixed conditions. And also, in order to determine whether Kirkendall effect happens, so you know there are two characteristics to demonstrate the Kirkendall effect. The first one is the plane shift. It's going to shift to the upside direction of the faster moving species. And the second one will be the void formation. Then that will be the result of condensation of excess vacancies, which means the vacancy will accumulate growth to form a void. So we're going to move to the second sections, electron migrations. Based on this term, you know, actually we have the electrical field, and this electrical field is going to drive the atomic migration. So in the beginning, we are going to give you a quick definition for the physical concept of electron migration. And also, we are going to show you how to quantitatively describe the effect from this electron migration and in different material systems. The first one we are going to talk about is the interstitial charged ions in ionic materials, which means we are going to have some dopant at the interstitial site, and this dopant will be the ion. So we dope some charged ion at the interstitial site in ionic materials. And the second material system we are going to talk about will be focused on the metal. So can be we have some interstitial atoms in the metal, and we also will discuss about if these atoms are at the substitutional site, how to quantitatively to describe the effect, the EM, electromigration effect. And before we end these sections, we are going to give you two case studies. The first one we call the EM pledge effect or short stripe effect. And the second one is we call the current cloudy effect. Actually, both these effects are a negative effect in semiconductor industry. That means we don't want this happens, because as long as this happens, you will observe lots of voids form into your materials, and as long as this void get bigger and bigger, and that will destroy or allow your device failure. So this actually we don't want this happen. In order to understand the mechanism why EM happens, then you have chance to overcome or avoid this effect. So this is the purpose why we need to learn the electron migration. And here the very important um, um, flux you need to focus on or pay attention would be because in most of case you apply the in this case actually we have a two driving force, right, in these sections. The first one is the electrical field, and the second one we talk about is the diffusion, right? So will be the atomic flux. So based on the flux force equation you learn from the lecture 1. So I believe you can simply write down the flux J1, atomic flux, and the current density in this case. When you have two driving force, included the electrical field and the chemical potential gradient, is a possible driving force, right? Okay, so let's move to the first one. We talk about the ionic materials. So now we have a charged ion at the interstitial site in the ionic materials. Okay, so what we have here, in order to answer what's the electromigration, what's the effect due to the electromigration. So first of all, you need to identify the material system we're going to talk about. So here we talk about the ionic material. So we consider we have an ionic material, and inside these materials, they have the dilute concentration of positive charge ion that diffuse interstitially. That means these ions are located at the interstitial site, and they will diffuse through interstitial sites. So let's take a application for this this idea. This slide will be lots of people deal with the want to synthesize the electrolyte in solid state battery. So most of them will use the doped ionic materials. So in order to understand or prove the quality or properties of these solid electrolytes, you use by using these ionic materials. So you need to learn this idea. So let's move back here. So we have an ionic material. So let's take the zinc sulfate as an example. Zinc sulfate is ionic materials, and in this ionic material, we also have the copper ion at the interstitial site. Then we are going to apply the electrical field on these materials. So as long as I apply the electrical field on these materials, then what will happen? This copper ion is going to move due to the electrical field, right? And it is a positive charge, so it will toward to the cathode side. Okay, so now you have some idea about the material systems we're dealing with. Then next, we hope you can write down the driving force, the flux of these interstitials, and also what's the electrical conductivity of these doped ionic materials. Okay, so driving force. We start from the driving force. The driving force, as you know, is the minus potential. You can take the is a potential gradient, minus potential gradient, right? So, in order to know the driving force here, what's the potential of this positive charge ions? So, here the potential here is the chemical potential of this charge ion. And due to we apply the electrical field, this copper ion is going to move inside this electrical field. So you have extra electrical potential turn. And Q1 here is the charge of diffusing atom. Here is 2 positive charge and times the electrical potential you apply on these materials. So some people probably were curious about why the potential can express like this is a chemical potential plus the electrical potential. So we move to next slide. Under these situations, this potential actually people call it as an electron chemical potential, and it's open. Most of when we electron chemical potential usually is discussed in the ionic systems. Let's definitely have a mass transport in ionic systems. Why? Because when you apply the electrical field on the ionic material systems, then the ion is going to move inside this electrical field. So you will cause the extra potential, electrical potential, be generated during this diffusion process. So you not only have the atomic movement. For example, like probably you will move. There's 2 atoms move. Probably there are 2 atoms move to this side, right? But because there's moving under the electrical field, so you need to consider the driving force. Also, we consider the electrical potential part. So now, in order to know the Rayleigh relationship, so we will have some we need to describe some conditions, boundary conditions here. So one intrinsic constraint means the dq, the total change in charge, equals to the charge carried on that carrier times the change in the concentration of that diffusing ions, right? And so if you want to know the total potential, you can sum up all the potential function times the physical entity together, then you will get the total potential part, right? So so based on this concept, the first potential we deal with would be the chemical potential part. So you can simply write down the mu1, the chemical potential of atom 1 times the change of the concentration of atom 1, dC1. This is a chemical potential part. And due to this is ion, when some ions move from this way to this way, not only the change in chemical potential and also will induce some and generate some electrical potential due to you apply the electrical field on it, right? So the electrical potential be generates the phi dq. Phi is the electrical potential times the quantity is dq, depending on how much charge moving through this electrical potential, right? Okay, so based on this, dq actually is the dq here. So we substitute the q1 times the dc1. So we take the dc1 out, and we put the other items together. So you got the mu1 chemical potential plus the q1 times the phi, and this is due to the this is chemical potential, and this is due to we apply the electrical field on it. So the driving force actually we just take the gradient minus gradient of the potential turn. So we take the gradient on this term, so you know that electrical potential, you can combine this potential including the chemical work and also the electrical work. So let's move back to the previous slide, so you know why we can use the chemical work and put the chemical work and electrical work together to substitute to get the total potential work. So next, in order to get the flux of interstitials like this copper ions, and you have a driving force. So don't forget how to write down the atomic flux as long as you have the driving force. The first part is due to the diffusion, so I use the fixed first law minus the diffusivity concentration of these diffusing atoms to substitute the chemical potential part. And the second term actually is due to this driving force, right? So we all know the driving force is take this gradient term. So will be the mobility, concentration, and the driving force. This driving force is here. Minus Q1 is a constant. You take this out and take the gradient on the electrical potential. So we got this. So we get the flux of interstitials. And yes, based on previous slide, we know that you should write down the flux of interstitials, right? And also you need to write down the current density. The current density part, okay. So if you try to write down the current density part, it definitely will obey the Ohm's law, right? Like this. Potential gradient. Okay. So you will get this is Ohm's law. Current density will be equals to Ohm's law, right? So you successfully, before we move forward, you successfully to get atomic flux and current density. But at this stage, we still, yes, you get the atomic flux and the current density. But in these ionic conductors, there's some relationship between these two, right? Any relationship? Because usually the conductivity in ionic material is quite low, right? So if you have a current density, definitely is due to this these stopped charge ions moving through the electrical field you apply on it, right? So there's an additional relationship between the atomic flux and the current density. It will be the charge, two positive charge here times the atomic flux. So we just use this to substitute the J1 by using this. In order to simplify these questions, we assume there's no significant concentration of this doped positive charge. So we can delete this term. So you just times the Q1 with the times Q1 to times this term. So we'll get the here. So in this case, we know we can expand the electrical conductivity for this doped ionic material is dependent on the diffusivity of this positive charge ion move into these materials. and also the concentration of this charged ion, also how much charge it carry on this doped ion, and also the working temperature. So we know the electrical conductivity for these ionic conductors is related with these parameters. So in this case, you can tune or control the conductivity of ion materials to reach to have the highest conductivity in ionic materials. So in order to prepare the good solid electrolytes and used in battery, so you expect to have a higher electrical conductivity. So what you can do here is you can think about how to increase the diffusivity, or you can increase the concentration of this positive charge ion, or you can increase the charge carry on this ion, or increase the temperature. This is some suggestions to help you, some comments or suggestions to help you to know how to increase the electrical conductivity of the ion material.